Okay, let's look at some psychophysics. Now, this is how we, as linguists, look at the sort of the psychological transformation of physical physical things out in the world into our perceptual impressions of them. Right, and we're going to look at three of the acoustic characteristics of sound. We're going to look at frequency, amplitude, and duration. And for each of these, there's a perceptual correlate. And I don't know if this is good or bad, but the technical terms are actually common words. And so they're words that are familiar to you, but we're going to use them in a very specific and careful sense in this last portion of the course. So for frequency, the physical characteristic of how many times does something repeat every second, measured in hertz typically, the perceptual correlate of that is pitch. So when a phonetician talks about pitch, they're not just casually using a shorter form of the word frequency. They're talking about a different phenomenon when they're being careful. We're not always careful, but technically that's what it is. So frequency, usually measured in hertz. One of the things that we do is we can log transform that, because that seems to get a lot of the way to how we perceive sound. Log transform, we know from looking at decibels as a way of representing amplitude. So it's still technically a physical measure. So log transform of frequency is still a measure of frequency. And the two scales, two sort of paired scales that we use, are the octaves and the semitones. So an octave is just a doubling of frequency. So every time the frequency doubles, you add one octave. Doubles again, one more octave. So, if you quadruple your sound, your frequency, you've gone up 2 octaves. If you multiply your frequency by 8, you've gone up 3 octaves. Now, doubling is a big change, so we often use semitones, which is just 1/12 of an octave. So 12 semitones adds up to a doubling of the sound. And there's a formula for that. It's given in the textbook. It's given in the notes for this section. It looks a lot like the formula for transforming amplitude in, say, pressure, like pascals, into amplitude as a decibel measure, because it's the same kind of transform. There's different numbers attached to the constant out front and the base of the logarithm, but it's basically the same idea. Multiply some number times a logarithm of the thing you're measuring divided by a reference thing, and there you go. Okay, so yeah, octaves and semitones still measure a frequency. It is pitch-ish in that the reason we go that way, the reason we use semitones, which you do see sometimes in phonetic literature, is because it is starting to connect to, it's closer to how we process speech perceptually. To get a proper perceptual measure, we have to go out and do a bunch of working out how people hear something. And so that gets us to the MEL scale. The MEL frequency scale, MEL pitch scale, I beg your pardon, is calibrated by getting people to listen to one tone, a reference tone, and then saying, okay, if we move that tone down, when does it become half the pitch of that reference? If we move it up, when does it become twice the pitch of that reference? And you can do that with a bunch of different reference pitches, and you end up with a map of how frequency relates to pitch. As frequency increases, how much is the pitch increasing? The MEL scale uses 1,000 hertz as a reference point, and it says 1,000 hertz equals 1,000 MELs. And then 500 MELs would be not necessarily 500 hertz, but whatever frequency sounds like it's half the pitch of that 1,000 hertz tone, and similarly going up and back and forth. And so we have a formula that approximates, that gives us a fairly good idea of when you do this kind of testing over many people, this is about where that goes. So okay, if it goes up by 5 MELs here, that's the same perceptually as this 5 MEL difference up here and so on. So it's this sort of isomorphic, it's changes of similar pitch, which does not map to changes of similar frequency in terms of hertz or in terms of semitones. Okay, that's all well and good, but the sounds that we listen to aren't all pure tones. The MEL scale is completely calibrated to pure tones. And one of the things that happens when you have a complex sound is you don't just have relative levels of pitch, relative levels of fundamental frequency and the pitch corresponding to it. But you also hear other elements. You hear the complexity. That's why E and A, even if they have the same fundamental frequency, sound different because our ears can detect other frequency components. But if two frequency components are too close together, there's a point after which we can't tell them apart perceptually. And that's called a critical band. And at low frequencies, that critical band is really narrow, right? Two sounds have to be really, really close together for us to not be able to distinguish them. At higher frequencies, they can be a little farther apart, and so on. So critical bands are part of our perception of pitch. And so the bark scale, and derived from that and sort of expanding on that, the ERB, or equivalent rectangular bandwidth scale, these are two scales that do what the Mel scale does and give us an idea of relative pitch, as well as indicating, what are these critical bands? What's the bandwidth of this sort of masking effect where, if you have a sound here, you're not going to hear one next door as distinct. So those are our three pitch scales that we've got: the Mel scale, the bark scale, and the ERB scale. And we have formulas for all of those in the textbook that you can have a look at and play around with if you are so inclined. All right, there's pitch. Now, what about loudness, right? So we have frequency, acoustic, pitch, perceptual. Amplitude is an acoustic feature, and loudness is its perceptual correlate. Loudness is what we hear, amplitude is what's out in the world. And this is even more complex because a sound that has a particular amplitude in terms of pascals or in terms of decibels isn't going to sound quite the same loudness as a sound that has the same amplitude but a different frequency, right? Our ears are more sensitive to a certain band of frequencies than to things below that and above that. So, for example, a 1000 hertz tone might sound, middling loudness. But if you go really low, if you go down to 500 or go down to 100 hertz, that same amplitude is going to sound quieter because our ears aren't as sensitive at 100 hertz as they are at 1000 hertz. And similarly, if you go way high up to 10,000 hertz or 20,000 hertz, that same amplitude is going to sound quieter because our ears aren't as sensitive up there. Of course, my ears are especially unsensitive because I'm older and continue to get older, fortunately, with each day. And so aging is one of those things that gives us some hearing loss, and there are other things that can do it. Anyway, so if we want a perceptual scale for loudness, one thing we need to do is find out what that equivalent loudness is. Like if I have to change the amplitude to get the same loudness, well, I want to map that out. And that's where we get a map like this. So we have a reference tone at 1000 hertz, and say we get one at 50 decibels. Here's a tone, and then we go down in frequency, and we say, okay, well, what amplitude do we need a 500 hertz tone to be at in order to sound as loud as our 1000 hertz 50 decibel tone? And all across the frequency scale, and as we find those points of equivalent loudness, we can draw these lines. And for each different level of amplitude at 1000 hertz, we can draw a separate equivalent loudness line. And you can see, I'm going to switch back to this. We'll come back to that. You can see that in the range where, if you look in the textbook about what does our auditory system really like to reinforce, what are the ranges that the auditory canal, the ear canal, really likes to promote, the transmission through the ossicles really works well for certain frequencies, and so on. Those are the sounds that are at the bottom of that curve, where we're really sensitive. It doesn't have to be that loud for us to perceive it. And then outside of that, it has to get louder and louder for us to perceive it as the same loudness. The Phon scale, PHON, is what we see here. So if you take the reference frequency at 1000 hertz, 10 phons is any sound that is equally loud, that has the same loudness as a 1000 hertz 10 decibel tone. For a sound to be 20 fons, it has to be as loud as a 1000 hertz 20 decibel tone, and so on. So we have these equivalent loudness bands. What the font scale doesn't guarantee is that the relative changes in loudness are equivalent. So a 10 fon difference from 10 to 20 fons isn't necessarily the same perceptually as a 10 fon difference from 50 to 60 fons, for example. Okay, so how can we fix that? Well, that's where the SONE scale comes in, S-O-N-E. And S-O-N, the SONE scale basically takes these equivalent bands, that's fine, just gives them different numbers. So the reference there is the 40 fon equivalent loudness band. That's one SONE. 40 fons is one SONE. And the SONE scale is calibrated, so every increase of 10 fons is a doubling of the SONEs. So from 40 to 50, 50 fons is 2 SONEs. 60 fons, 4 SONEs. 70 fons, 8 SONEs, and so on. And it turns out that then a difference of 1 SONE here versus there is approximately an equivalent difference in loudness. It sounds like the same amount that you're changing things by. Okay, so there's our loudness scales. And the last acoustic property that we transform into a perceptual property is duration. Duration, how long something takes to happen. I'm not talking about period here, that gets dealt with frequency, period of a repeating thing, but duration, like how long did it take to make this sound versus that sound. And the main perceptual thing that happens here is what we were talking about in the suprasegmental section, its length, right? Some languages have a contrastive length on vowels, on consonants, sometimes even on both, where, there's a short version and a long version, and the difference may be a doubling of duration. It may be a 1.5 times, maybe something else, but there's a difference that switches you over from one category to another category linguistically. Other languages, English does this, have a more allophonic difference. So we don't distinguish one word from another based on the length of we have a short phoneme versus a long phoneme, but you can have sounds becoming longer in particular environments, and that helps us perceive other aspects like the vowel quality or the consonant voicing or something like that. So the acoustic property, the physical out in the world property of duration, gets translated into the perception of length. This is a long or a short sound. Okay, so there's a lot happening there. There's a lot of different ways depending on the acoustic feature and how it works in the auditory system. We have to do different things to generate and understand the perceptual scales of those. So we have acoustic features of frequency, amplitude, duration, and we have perceptual features of pitch, loudness, and length. And there you go. And in the next module, we're going to be building on all of this awesome hearing and perception stuff to look at the perception of speech sounds. Cool.